In 9.1, we talked about probability as what you want divided by the total. Well, now we're going to talk about doing the same thing. We're going to do outcomes and events. Now let's look at a coin being tossed 3 times, and an outcome can be represented like a string as it shows HTT, meaning you get heads the first time, then tails the second, then tails the third time. There are 8 outcomes listed in this table. All the combinations of tossing a coin 3 times, all the possible combinations. So you're going to check the outcomes that are contained in the event. So the event, getting a heads on the last toss. You'll look through here. Well, this one, last toss. This one, last toss. This one, this one. There are 4 out of 8. That's 1/2. You've got a 1 out of 2 probability because what we want is heads on the last toss out of the total possibilities. Okay, let's look at the next one. Alternating tails and heads. It doesn't matter which comes first. So heads, tails, heads works. Tails, heads, tails works. There's no more alternating. That's 2 out of 8, which is 1 out of 4. Then for this one, exactly 1 tail. Well, to have 1 tail, you got to have 2 heads, right? But it doesn't say where. This is 1 tail. This is 1 tail, exactly 1. This is 1. 3 out of 8. And that's 3 out of 8. Can't be reduced. That's what you're going to do on the charts. You're looking at the case where you've got all the options presented to you and you choose the correct option. Now here, when we do probabilities, 1 second. Yeah, sorry, it's checking. Probabilities with 2 dice. What that means is we're going to add the dice. And so let's do a couple things on here to make it clear. What you roll okay, first die and second die. So the probabilities of 2 dice when you're adding them. If you look, how many possible ways are there to roll 2 dice? Well, go back to last lesson when we had the fundamental counting principle. Well, if you roll a die one way, 1 die, you've got 6 possible outcomes, 1 through 6. If you roll a second die, you've got 6 possible outcomes, 1 through 6. So if you roll 2 of them and you add them together, there are 36 possible outcomes. And that's on that little dice chart. There are 36. So let's see. The sum is greater than 7. You know how you do this? Really complicated math, guys. I look at my chart. That's greater than 7. Oh, that's greater than 7. I count. I literally look and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 outcomes greater than 7 out of 36 possibles. Reduce it, 5 out of 12. I expect you to reduce. Okay, the next one. The sum is not divisible by 4. Not divisible by 4. Well, you know what that is. That is, my blue, all your odds plus more. Let's do it the simple way. How many are divisible by 4? Well, looking at my dice chart, you're looking at numbers 4, 8, and 12. Those are the only numbers that are divisible by 4. The others are not. So let's count how many times you can possibly roll 2 dice that add up to a 4 or 8 or a 12. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 total. So we're going to do it the easy way. If there are 9 total possibilities to get 4, that means there are 36 minus 9 possibilities that are not 4. And there we go. 25 over 6 is the probability for event B. Go to the next page. Okay, oops, it's a little, hold on, it's a little, let's do another one. And I know this looks a little wonky. On your notes, everything's on the same page. So let's do this one. You try it. I want you to stop the video, I want you to practice, and then start it up again, and I'll have your answers. All right. So here, the sum is less than 6. It's 2, 3, 4, and 5. Because it's less than 6, not equal to 6. Count all the blues. I think there's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 out of 36, which reduces to 5 out of 18. Now let's do one where the sum is divisible by 3. So those numbers are, we'll write them here, 3, 6, 9, and 12. So you're looking for 3, wherever there's a 3, wherever there's a 6, and a 9, and a 12. So let's count the green dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 green dots. 12 out of 36, that equals 1/3. There's a 1 out of 3 probability. Okay, next page. Okay, theoretical and experimental probabilities. The only difficult part of this is understanding the terms. Theoretical, as it says, is what we expect to what we expect to happen. Probability or experimental is what actually happens. So you could expect that you have a 1 out of 2 chance of getting heads every time you toss a coin. That's the theory. But at the experiment, you may get heads 4 times out of 5. So let's take a look at the lottery board, because this one can be tricky. You got the machine, hold on. They're examining the machine that randomly picks lottery numbers. You definitely want this one to be valid. On each trial, the machine outputs a ball with one of the digits 0 through 9 on the ball. Okay, so let's see, and this would be the digits. And how many are there? 10 of them. Between 0 and 9, there are 10 digits. And when you get one, the ball is replaced in the machine, because this is just verifying whether it's valid or not, okay? So the lottery board tested the machine for 40 trials and got the following results. Now you're rounding your answers. This is number of trials, and that is 40. Assuming the machine is fair, what is the theoretical theoretical probability of getting a 3. How many 3s are in the list of digits? There is 1 out of 10 numbers. That's the theoretical probability of getting a 3. But what was the experimental probability? What actually happened? Well, look at it. For number 3, 1. 1 out of 40 times. Oh, I apologize. This should be in decimals. My fractions aren't wrong, but I forgot it's supposed to be in decimals. So let me fix that really quick. All right, this probability is 0.0. Oops, my bad. You have 1/10 of a probability, 0.100. Now this probability is 0.025. So let's do the last question. Assuming the machine is fair, what statement do you think is true? With a smaller number of trials, it's surprising when the experimental probability is greater than the theoretical. With a small number of trials, it is not surprising. Or with a small number of trials, the experimental probability will always be much greater than the theoretical. Well, let's take a look at this. Is our experimental probability greater than the theoretical probability? It is not. That one's out. Assuming the machine is fair, is it surprising when the experimental probability is greater, or is it not surprising when it's much greater? It is surprising when it's greater, because here's a rule. Well, it's up right there. The larger number of experimental trials, the smaller the difference between theoretical and experimental probabilities become. So if we ran 400 trials, our experimental probability would be closer to 0.100. So based on the statement above, with a small number of trials, it is surprising when the experimental probability is much greater. That is unusual. We're not saying it is greater because it's not greater. 1 out of 40 is not greater than 1 out of 10. But it is surprising when it is greater. Okay, last page. Spinning a spinner. I'll make this bigger for my notes. Now there's something nice about a spinner. A spinner doesn't really move. I mean, and the pieces stay the same. So we're going to do, again, theoretical and experimental probability. You got 10 side slices and spun the dial 500 times. So you got white 189 times, gray 162, black 149 times. So we're going to assume the spinner is fair, compute the theoretical probability of landing theoretical. Landing on a black or a gray. Well, there are 3 black and 3 gray, 6 total out of 10, 0.600. Okay? She has a 60% chance, or a 6 out of 10 chance, theoretically, of landing on a gray or a black. Well, let's see what reality says. What did she land on, a black or a gray? Well, 162 black or gray plus 149 black equals, I'm going to do this one in my head, 311 out of 500, and that equals 0.622. So let's ask questions again. The smaller number of spins, the greater likelihood this experimental probability will be close. The experimental probability will never be close, no matter how many spins, or the larger the number of spins, the greater likelihood that the experimental probability will be close. It's the bottom one, because that's what it says on the previous page, or possibly the top of your page notes. The more numbers of spins on a spinner, the more numbers of rolls of dice, the more balls are generated by a machine, the closer you get to the theory. All right? Well, that wraps up 9-2.